Okay, so before we start, okay, where is it? Okay. Where is it? Okay. Previously, we take a look at this example, right? And in the off stream, I realized that I'm doing something like this, which is not correct, It should be like this, not the address of x, but the value from the pointer x. And this kind of, what is it called? Give us some, not this one. Give us some, what is it called? Some new information, I guess, that casting can hide the compile time error, maybe something like that. Okay, this one, and then this one. Let me copy this. Okay, see, it looks fine. Now if we remove the casting like this, right, it becomes an error. Incompatible pointer type. So because of the ampersand symbol, it becomes a pointer to pointer instead of just a pointer. So we should remove this ampersand like this, right? And then now we got a warning about the discard const qualifier. So there's a little bit of information there about the casting. We should be careful using the casting because it can hide the compile time error like this one. Incompatible pointer type, right? Okay. And then let's continue. Let me open the table of content to if I remember correctly, we are still in section 5.4, this one. So let's take a look. Where is it? Okay, this one. Previously we learned about, what is it called? The reason why separation between fork and exec for creating new process is essential, right? Because it is the essential part, or maybe the sign, if is that the word? Anyway, it is the essential part in building a unique cell like BASE, ZSH, TCHH, I think KHH2, yeah, any unique cell or DES, right? If you ever use this, I think the Debian shell, I'm I'm not sure. Anyway, the building part of the Unix shell, because it lets the shell run code after the call to fork, but before the call to exec. So if we take a look here, oh, and by the way, where is it? If we try to run this one, where is it? Playground. I think this one. If we try to run this one, right, we are basically trying to change the character inside the string literal, which have a static storage duration and read-only memory. So this way we have cons, right? And if we do this, we will get a segmentation fault. Let me put this in here, see, get a segmentation fault. So what we do in here, not this one, maybe in this one, in the exec VP, might be fine. I mean, I'm still not sure what the implementation of exec VP here. So maybe in some scenario we will, what is it called? We will modify the character inside the argument. Again, I'm not sure what is the implementation here. See, it is a pointer to char, not a const char, to keep something in mind. Okay, let's go back to here. So previously I have some, what is it called? I have some hypothesis, right? Maybe this is what happened about this, what is it called? About this explanation, right? Run code after the call to fork, after a fork, but before the call to exec. So maybe, let's say we try to run the WC program or executable. We use wait, right, to wait the program to finish, and then at some point we call fork system call to, what is it called, to duplicate the process into the child process, and then inside the child process, right, we are calling exec, which means that we are replacing the instruction in the child process with the WC process, as far as I understand. And then after the WC instruction finish, we are going back to the parent process because of the wait here. So it is, where is it? Something like this maybe. But yeah, instead of using with system call, we are using with PIT instead. Okay, and then let me try running that. Chapter 5, page 3. Okay, maybe something like this. We start the, what is it called? We start the program, let's say, and then we are going into the chat process and run the program in the chat process. And then we are going back to the parent process. This one to printf. That is my hypothesis about this one, which means it can be wrong. Just to put a disclaimer that this code can alter the environment of the about to be run program and thus enable a variety of interesting features to be readily built. The cell is just a user program. Okay, so here a prompt, right? Okay, in my case, this is my prompt, the highlighted one. But if you're using bash, you make see this prompt instead. Okay. You can type a command, the name of an executable program, plus any argument into it. In most cases, the cell then figures out where in the file system the executable reside, usually using the path environment variable. But maybe there is another source to check where the executable is, and then call fork to create new thread process to run the command, call some variant of exec to run the command, right? And then waits for the command to complete by calling wait. When the child completes, the child process completes, the cell returns from wait and prints out a prompt again. Prints out a prompt again, ready for your next command. The separation of fork and exec allow the cell to do a whole bunch of useful things rather easily, right? With the redirection, you know. So this means that we are passing the output from WC program into the file new file.txt. Well, I can show you, I guess. Z30P3, okay, this one. Let's call it file.txt, right? And then if you take a look, comes something like this. And it also, what is it called? In case you have found this syntax, right? As far as I understand, this is basically the same. Right? I mean, this, what is it, greater sign, and this one greater sign is the same. I mean, by default, as far as I understand, the greater sign will use the standard input, standard output to for the redirection, and also we can use the, what is it called? We can use the another file descriptor, I guess. For example, P3, okay, not that one, something like this maybe, the standard error. In case you are new, STT_in or standard input is equal to 0, and then there is the standard output, right, equal to 1, and then there is also the standard error equal to 2. So if we do this, maybe let's try triggering an error, something like this. File.txt. Okay. See, we didn't get any error message because we are passing the error message into the file. But if we do this, right, we got the error message. And let's take a look at the file. It's empty because there is nothing in the standard output. Now let's try this one, file.txt, okay, and then get file. See, this is the error message that we are passing to the file. There's a little bit of information, and yeah, I kind of forgot where is the file descriptor reside. STT_in file descriptor. I mean, currently I'm still not really sure about the file descriptor. I think it is called FD. No. Yeah, I cannot forget. Where is the standard input, output, and error? Yeah, it is somewhere in the system. Wait, maybe I can take a look at file hierarchy here. Okay, no. Well, anyway, let's continue. In the example above, the output of the program WC is redirected, right? If I remember correctly, the official term, the terminology for this greater sign symbol is redirection. So you can check this. Cell redirection. Unix cell redirection. Maybe something like that. This is the manual for the redirection. see. Let me copy this in the chat in case anyone wants to take a look. We are passing in this case, right? Oh, tier list. Okay. If I understand correctly, we are passing the error from the standard error to the standard output. The order of redirection is significant. Direct put standard output file descriptor 1, right? That's why it is 1, or well, the default standard, the default, what is it called? Redirector? Is that the word? The default redirection is 1, the standard output, if we didn't specify any file descriptor, such as 1 or 2. I'm not sure if we can use 0, the standard input, I haven't tried that. Direct put standard output and standard error to file descriptor 2, this one, to the file tier list. While the comment, okay, this one directs only the standard output to file tier list. Okay, interesting. Yeah, I haven't tried this. So we have a file tier list, right? And then we are using redirection after the file. I mean, I've tried something like this, if I remember correctly. And yes, it only put the standard output. But then again, we are replacing the standard output with the content from the standard error. Okay, because the standard error was made a copy of the standard output before the standard output was redirected to tier list. Okay, maybe we can try that. Something like this, right? Which doesn't exist. Okay, if we run this, we will get an error, right? But then we are redirecting the standard error to the standard output. Okay, let me put this in here. The in is 0, and then the out L, okay, something like this. Okay, we are redirecting the standard error content to the standard output, something like this, and then we are redirecting the standard output to file.txt. Okay, that is not what I expected. Okay. Are you using Tmax? Yes, this is Tmax. This one. I am using Tmax. So that's again. Let me try understanding this. Maybe something like this, but yeah, that's not the case. Directs only the standard output to file tier list because the standard error was made a copy of the standard output before the standard output was directed to tier list. Maybe trying something like this. Let's find out. Or let me try something like this. Okay. And then what is the file? Okay. Interesting. I mean, if we do something like this, for example, yeah, I'm not really sure. We're copying to the standard error, right? And then trying to redirect the standard error to the file. If I do this, it's still still there. Wait a minute. Let me try again. When we're having an experiment. Okay. Something like this. But we're still printing that. Okay. Empty. Alright. So looks like we are, what is it called? We are redirecting the standard output first, and then we are doing this. Is that how it works? I am not sure. Okay. We cannot do that. Yeah, this is an interesting case. So maybe I haven't tried this one yet. Oh, right, this is where the file descriptor is, if I remember correctly. Not this one. Okay. See, 0, 1, 2. And well, if we do this, okay, cannot really see that. 0, 1, 2, the file descriptor, and then maybe 3 is for the ls. I'm not sure what the 3 in that means. Okay, maybe we should try using the ls. I'm kind of curious. File.txt, okay. Alright. Okay. Oh, this is kind of interesting. So we are creating the file first and then using ls. And let me remove this, right? Okay, there is no, what is it called? There is no file.txt. Okay, and then file.txt. What is that? Okay. This is kind of interesting. So file.txt might be created first before we are running the ls. Because again, previously there is no file.txt. And then now there is a file.txt. This is kind of interesting. So we migrate the file first and then running the ls. And did we ignore this? I'm still not sure. Okay, maybe let's try this one out. Direct put standard output and standard error. Okay, let's find out. Okay, let me remove this, right? And then file.txt 1. Okay, file. Alright. I am still not sure what is going on. Let me try with WC program or executable, I guess. I mean, this should be an error because again, we don't have p3.c in the current directory. What happened? Okay. .txt. Alright. Okay. Interesting. So, okay. If I understand correctly, we are finally moving the, what is it called? The standard error to the standard output, and then passing that standard output to the file. I mean, if we do this, right, only this redirection, the standard error still have a content, right? And if you do something like this, let's try. Okay, file.txt. Alright. So if there is no content in the, what is it called, in the standard error, the standard output is still there. Is that it? We still using the standard output. I mean, again, if we do something like this, right? It become empty. So So this is kind of interesting. And yes, I'm still not sure about this one. Okay, nice. I never use it. Oh, okay. I mean, it's quite nice using Tmax, you know. Let's say I accidentally close my terminal emulator, right? And then I can just resume where I was left. Going back to the same session. Alright. In the above example, the output is redirected into the output file, new file.txt. The greater than sign is how said redirection is indicated. Right, this one. The greater sign is the redirection symbol or instruction, maybe that's the word, or indicator. Anyway, it is the redirection symbol. The redirection instruction, maybe that's the word. The way the shell accomplishes this task is quite simple. When the child is created, before calling exec, the shell specifically the code executed in the child process, right? Close standard output. Well, in this one, right? Close the standard output and opens the file, new file.txt. By doing so, any output from the soon-to-be running program, WC, is sent to the file instead of the screen. Open file descriptor or keep open across exec call. Thus enabling this behavior. Okay. Right. If I understand correctly, maybe it is something like this. Prom, right? The cell prom, and then let's just pay for .c, right? And then we, what is it called? We redirected to file.txt. So, okay, this is wait, what is it called? Wait the program to finish, okay. Program to finish, and then fork, right? To the child process. To the child process, and then maybe during this time, yeah, I mean, what is it, before calling exec, right? Before we are replacing the shell instruction with the program instruction, maybe in this one we are using open, I think. Wait a minute. Let's open this in this one. Okay, we also have the POSIX standard. Okay, maybe something like this. Open and possibly create a file. Okay, maybe in this case we are calling open to open or create file.txt, something like this, and then close, right? And then close standard output. Okay, so it's quite long. And close stt out, and then we are replacing the instruction of the shell with the instruction of the program, like this. Exec in the child process. In the set process, and put the output into file.txt instead of stt-out, and then we finish the process. Return to run process when finished. Maybe something like this. So at some point we are still executing the shell instruction, right? With the open and close. Oh, that make me. Is there close? Oh, close a file descriptor. Okay, there is a close function or system call. Maybe that's the right term. Close system call, close file descriptor. Okay, open or create, and then close stt-out file descriptor, and then we are executing that with another file descriptor. Maybe that's the word. With file.txt file descriptor instead of stt-out descriptor. Instead of stt-out file descriptor. Okay. And then after finish we return to the prompt. This is my hypothesis. And I'm still analyzing this. What is it called? This statement right here, right? When the child is created by fork system call, and before calling exec, the shell specifically the code executed in the child process, right? So we kind of have some, what is it called? A duplicate of the shell, because of fog. I'm not sure which instruction that we are duplicating after the fog, but we have the soup cell or the fog of the cell, and in this fog we close the standard output and opens the file. We close the standard output file descriptor. I'm not sure if we can learn about file description or file descriptor. No? Okay. Or maybe it used different term. I am still not sure. Okay. We will see. Okay, close the standard output file descriptor and open the file new file.txt. By doing so, any output from the soon to be running program WC is sent to the file instead of the screen. Instead of the, what is it called? Instead of this one, standard output file descriptor. Duplicate file descriptor FD. Duplicate. Oh, there's different device. Okay. Interesting. Redirection using file descriptor greater than 9 should be used with care, as they may conflict with file descriptor the cell used internally. Oh, okay. The cell also use file descriptor, right? So we are replacing the file descriptor we use in the cell. Something like that. With file descriptor, oh, maybe something like this. With file descriptor file.txt instead of, yeah. With file descriptor from file.txt instead of the standard output. I mean open. Okay. The return value of open is a file descriptor, a small non-negative integer that is an index to an entry in the process table of open file descriptor. So when we open, right, we are actually opening the file descriptor too, if I understand correctly. Okay. Open file descriptor archive open across exec call, thus enabling this behavior. Open file descriptor archive open across exec call. Oh. Okay. Right. Previously I didn't realize that when we are using exec system call, is the file descriptor gonna change or not? And it looks like the file descriptor will be keep open across the exec call. Maybe it is related to the process itself rather than the instruction, right? Okay. File descriptor will be kept open across the exec system call. Okay, and then the question is, does that mean the file descriptor attached to the process instead of the instruction, maybe instead of the program? Does that mean the file descriptor attached to the process instead of the program? I mean, we are using the same chat process, right? We are just replacing the instruction inside this chat process. And well, if the file descriptor keep open, maybe the file descriptor itself is attached to the process, is the part of the process instead of the part of the program. Maybe to make it easier to understand, let's assume a process is a container, right? Or maybe something like this. There is a process, and this one is the instruction, or maybe program instruction, something like this. This can be, what is it called? This can be shell, and this can be wc p4.c. Anything can be in here, but this is the, what is it, the container or the process that we are creating. So we are only replacing this one. Maybe something like this would be better to understand. Yeah, let's use base to make it even easier to understand. We have base, and then we have instruction for wc p4.c. Thing like this, maybe, like the process is some kind of container, and inside of container we have program instruction, either from the shell or base or another shell or another program or executable. Maybe. We will see if our hypothesis is correct or not. Again, I'm still assuming in here. Let's create the the source code, include STT. Okay, output. Okay, I'm not disconnected yet. I mean, when it rains, my connection become really unstable. So yeah, let's see how it goes. If I'm gonna be disconnected or not. Figure 5.4, page 8. Okay, this one, right? Oh, we are adding a new header file. Okay. And let me read this first. Figure 4.5 shows a program that does exactly this. The reason this redirection works is due to an assumption about how the operating system manages file descriptors. Okay. Specifically, Unix systems start looking for free file descriptors at 0. Alright. If I understand correctly, file descriptor 0 is standard input. Okay. Unix system start looking for free file descriptor at 0 from the standard input file descriptor. Okay. In this case, stdout file no will be the first available one and thus get assigned when open is called. Interesting. stdout file no. What does it means? Stdout no. Let me check. Linux open stdout file no. Okay. Can I read from what is except for output redirection. Standard output value. Okay, let's check this out. Okay, file. Let me copy this in the chat. Hello, ping pong boing, welcome. We are currently in this section. Where is it? In the 5.4 section, we are trying to figure out the motivation why we need to split the fork and wait system call to create a new process instead of just having one system call. What is it called? System call API. Yeah, we are trying to figure that out. And it looks like, okay, why the separation of fork and exec is, what is it called, is essential, right? It looks like one of the implementation of this separation between fork and exec to create new process is the Unix shell, one of the implementation of the separation. And then because, well, what is it? Let me think. And in the Unix shell, the code, the shell run the code after we call to fork. It is we are spawning a child process, but before we call the exec, before we are replacing the shell instruction with the program instruction. Okay, I've made some simplified illustration, something like this. So let's say we run a program called wc p3.c. Well, let's just call it wc, right? Let's say we call the program wc. We will wait the program to finish, and then after that we will fork the, what is it called, the instruction from the shell into, what is it, the child process, into another process, right? And then inside this child process or another process, we are replacing the instruction from the shell with the instruction of wc, of the program. And then after the program finishes, we are moving back to the shell. It is the parent process. So we are trying to understand the reason there, and currently taking a look at the redirection, something like this. Basically, to put it simply, we are putting the output from wc command into the new file.txt. The output of the wc command into the, what is it called, new file.txt. This is called redirection. Okay, and then oh man, I always miss your stream since I got lots morning class. I mean, you can check the vote if you're curious, you know. But yeah, I usually stream early in the morning. Okay, right, so, like some people said, programming first early in the morning, programming before breakfast, something like that. Yeah, I haven't eaten breakfast yet. In case anyone curious. Figure 5.4 shows a program that does exactly this. The reason this redirection works is due to an assumption about how the operating system manages file descriptor. Okay. Specifically, Unix system start looking for free file descriptor at 0. In this case, why is tt out file no? Okay, let me check. Tt out. Okay, so it is the standard output value. to find the file descriptor that shall be associated with the ceiling width STT in. Okay, so it is the standard output value which will, if the following POSIX compliant, then it is 1. If they're following POSIX standard, I mean. Okay. Will be the first available one. Why is STT out file now will be the first available one? That's what I'm curious. I mean, again, we also have this one, right? The standard input width is 0. So is the standard input not free, not available during the execution? There is no footnote. Let me check. Okay, did I already? Okay, I think I already put this in the chat. Now let's take. Oh no. And thus get assigned when open is called. Why STT out is the first, what is it called? The first file descriptor. Maybe something like this. When and where standard input out and error. Okay, let's check this one. Where first open and when and where when and where are the symlink. Okay, mid. Where is the code that does it? I assume it is in the Linux kernel source code, but I wasn't able to find where it happened even after a search in the. Okay. Please, if you're done voting this question, can you explain why? So I can make it better. Right, again. The feedback sometimes matters. I would really like to know about this question. Not easy to find the answer. I should ask over here. File system contract that are unrelated to process. Okay. Oh, proc self. Alright. Wait, is that why when we are using this, the long list, it is a symbolic link to the proc self? Okay, interesting. Let me do this. Is it also a symbolic link? Okay. I have no idea what that is yet. Enter the vector open file for a process. Okay, wait a minute. The VTS, okay. Okay, FPTS. I'm not sure what this means. Maybe one day we will find out. Where proc entries get created? What looks like to be so complicated. When a process is started, part of the work to perform is to create the data structure that manages the process file descriptor. Okay. And in common sense, and in common case, populate the descriptor 0, 1, and 2 with the pointer to its controlling terminal device. Controlling terminal device. Okay, some process are launched with those file descriptors linked a different device than a terminal, often to the null device. Some processes have one or more of these file descriptors linked to an interface that leads to another process, usually a pipeline, or to a file using redirection. Okay. Some processes have one or more of these file descriptors linked to an interface that leads to another process. To another process. Oh, right. Using the pipe symbol. In case anyone knew, it is something like this. Chapter. Right. So we are piping the output from ls as an input for grep command. You can take a look at the main page. If you want to know what grep is, so here, interface that leads to another process using the pipe or the pipeline, or to a file redirection, like, where is it? This one. Instead of using pipe, those, what is it called? This symbol, I'm not sure what it is called. I usually call the pipe symbol. But yeah, instead of this pipe symbol, we use the redirection symbol or greater than sign. While the parent process may make the function calls to open files or pipes for this descriptor before spawning the child process, the function calls to open files or pipes for this descriptor before spawning the child process. It's still the kernel that manages the data structure that tracks the file descriptor. If you need to know this kind of detail, a book on Unix or Linux internal can tell you. Okay, each process has its own individual list of file descriptor. Okay, looks like again this question, right? Looks like the file descriptor is attached to the process instead of the program. Okay, we can replace the instruction of the program in the process, right? So that is why when we are replacing the instruction using the exec system call, the file descriptor is still open. Each process has its own individual list of file descriptor, so there isn't some universal set of descriptor or device file that you can point to and say they were created at one particular date or time. There isn't some universal set of descriptor or device file that you can point to and say they were created at one particular date or time. The descriptor for a process were created when that process was launched. A new process are launched a lot, so file descriptor are being created all the time and destroyed when a process exits and the operating system cleans up after it. Okay. That will be obvious in the kernel source code. There's limitation, right? Extended tutorial style and well put don't fit well here. Okay. Let me copy this and that's it. If anyone wants to take a look, and maybe copy this in here too. Reference. Alright, I think I also want to okay, copy the this is the POSIX STTIN. Why is it so slow? Am I lagging again? Okay, well, then this one. Let me put this in reference here. Okay. Do I need the best redirection? Maybe direction. Next redirection. Okay. Oh, okay. This is the Wikipedia. This is the genome one. Copy this to in the reference. Okay. Maybe the redirection first and then the POSIX reference. Okay. Terminal. Different process ID. Oh. Proxef. Okay, let me check. Proxef. yourself, something like this. Okay, not that one. Okay. Directory that is a number. Yeah, I mean, this is the process, right? But a different terminal, different process ID. Maybe something like this. Okay. This is kind of different from the previous one. Okay, maybe this is the file descriptor for ls. Maybe there's 5. You know what? I'm kind of curious. Let me open new terminal emulator. Proc self-ft. Okay, let's see. Oh, okay. PTS6. Let me open again. Proc, what is it? Self-ft. Okay, interesting. So we are creating a new file descriptor. Every time we use different terminal emulator. Is it specific to terminal emulator or the shell? You know? Let me check. I mean, this shell process is should be different from this shell process, I assume. Okay, it is not really the terminal emulator, but the shell itself. If we open the terminal emulator, not that one, proc self-ft, okay. See, it increased again. So maybe I've opened 7 cell. Here, 7 cells so far. That's quite a lot of cell I open. Right? It is interesting. Or maybe it's not cell 2, but another program opening the file descriptor 2. Like maybe Vim. Maybe Vim also opening the file descriptor 2. That's why even though I use this cell 1, 2, this one, right, 3, 4. And what about this one? We are doing some exploration. Okay, this is the second cell, right? I assume. And so I put this in the background. Let's just exit. Okay, proc self ft. Okay, this is the third one. Okay, let's put this in the foreground, in the background, sorry. Proc self ft. Okay, this is the fourth one. The first one is TTY, if I understand correctly, which is running this GUI environment. And then this is the second one, right? And this is the third one. This is the fourth one, and this is the fifth one of the 5 descriptor. If I understand correctly, that is quite interesting. P4, okay, P3. Alright. File descriptor are being created all the time. Okay. Okay, where is it? Yeah, why is standard output will be the first available one? Basically itu independent. But standard output and standard error gets logged at terminal. Okay, STTR is not a duplicate of STTR. They work in parallel, independent and asynchronously. Oh, which means that in a race condition, you might even mismatch, as you say. One practical difference is also that STTR output will be ignored when you pipe your output to subscan command. Okay. Okay, right. We are redirecting the standard output to the standard error. Okay. I think we have to take a look at this one. Then go to the rabbit hole from there. Right, we are in the rabbit hole of fork and exec. Okay. kernel has nothing to do with the standard input-output beyond copying the open file descriptor from parent to child. So naturally, the first time this file descriptor are open is when the first process does it. Init, okay. Auto def null, oh, interesting. Okay, the source code directly. This one. Make null stdio. Okay, interesting. This might not be the answer you're looking for, since this file descriptors are actually never inherited. It's very careful to ensure that no process directly inherits stdio from PID1, which is the init system. So looking at, but well, looking doesn't actually does that and repeats the word. You'll find this pattern repeatedly. Right, okay. Oh, we can do this. Interesting. We're printing out the current process, I think. Hello, Lucy. How are you? I'm still the same, fortunately. What are you doing today? I'm taking a look at this, well, at the book, previous book, right? The operating system, 3 easy pieces. And in the section, the reason why we are splitting the fork and wait to create a new process rather than using one API. And one of the reasons for this separation is because one of the example of the separation, the benefit of separation between fork and exec to create a new process is the Unix shell, like bash and something like that, because it let the shell run code after the call using the fork, right? We are creating a new process, the chat process, and then we call the exec to replace the chat process with the program instruction. And that mechanism create an environment for the program to use, like a separate process for the program to use, which can be, which the program can tweak or something like that. And now we are looking at the redirection, this one. Basically it is, basically in this case we put the output from WC program into the new file. Okay, let me copy this in the chat in case you want to take a look to what are the system call. Okay, if I understand correctly, fork system call, what is it called? Like copying the instruction from when we call the system call until maybe the end of the function into another process. Usually it is chat process. I'm not sure if we can fork the process in an independent process, not the chat process one. But yeah, to make things simple, fork is basically creating a new process with the instruction with the instruction of the program that we are forking. For example, this one, right? We're calling fork in here, which means that we are start copying from here to the end, I guess. Maybe the P1 example is more accurate. Okay. This one, we are calling fork in this one, which means that we are copying this instruction and this instruction and also this instruction into the chat process. So if we run this one, P1, right? The start is not copied into the chat process because we are calling the printf before the fork, so it is not copied into the chat process. We are copying the chat process. We are copying the instruction to the chat process after we call the fork. It is this one, the return code, right? The return code in the parent, this one in the parent, and this one, the return code in the child. If the fork succeed, right? If there is no error when calling fork, the fork will return the chat process ID, the PID, right? Where is it? This is the chat process PID. And then in the chat process, it will return 0. So we are copying this instruction until the end. That's why executed run twice in here, right? Because we are copying into the chat process. In this example, the one I highlight is the one running in the chat process, not the parent process. And this one is the one executed in the parent process. So that is the fork and also exec, right? There's also exec. Exec, if I understand correctly, we have the process. We can think the process like some kind of container or maybe object. Some kind of container like this. We have this process, and inside those container we have the program instruction. So let's say that we have PIT69, right? Inside this PIT69, first we have bash running. Execute bash. Right? And then later on, again, we are still in the PIT69. We are replacing bash with WC. Okay, maybe let's use this what is it called? This illustration. Execute bash from WC before.c, maybe something like this. And then later on, we replace the bash instruction with the program that we're running, the WC program. Like, you know, when we run this, right? So we are replacing the shell instruction with the program instruction in the child process. We are replacing the bash instruction, maybe something like this, and then execute WC instruction later on. Exec replace instruction in the process. I mean, if I remember correctly, if I understand correctly, we can use exec in the parent process, so not using fork, but I'm not sure. Is there any disadvantage or not doing that? Okay, something like this when we are using exec. So that is the simple explanation about fork and exec. I mean, I'm also still learning, so this is just my hypothesis from the book explanation, which might be incorrect. Okay, and now I'm kind of curious why the standard output is the first available file descriptor and not the standard input. Why stdout is the first variable file descriptors and not stdin? Even though in is stdin file descriptor is 0. This is my question. Maybe I should put this question in the comment here too. Okay. Yeah, I haven't found an explanation for that yet. Maybe it is the default in the system call. So rather than starting from 0, you start from 1. So sequentially write by the chat process to the standard output file descriptor sampled by routines such as printf will then be loaded transparently to the newly opened file instead of the screen. Okay. Let me also copy this in the comment. Fork to the chat process. Okay. I'm still confused by this one. Why is it the first available one? Okay, let me check. Maybe cell redirection to STT input. Redirect standard input dynamically in PScript. I mean, can we do that? Theoretically, if I know the PID of parcel, if I know the PID, the process ID of base cell which is running, can run a cat whose STT out is redirected to the STT in of that cell. It seems to be as if I type something on the cell. Unfortunately, there will be stream coming from cat. Okay, right. Symlink, right? Or whatever the data comment give you. Return terminal A and comment. Enter will run on terminal B. An interesting race condition. Make it seemingly random. Each cell gets a character. To reader for one input are compete for the data for the same stream. Okay, interesting. Exact 0, huh? But this is not the one that I need. Oh, okay. Standard input, right? listen for information. If you type cat with no argument, it listen for input on std_in, outputting what you type to standard output until you send it an NO file character to control T, right? As you can see, with standard input, set a string to a comment directly. Is it because open only what is it called? Only looking for the output file descriptor. I'm not sure. What is the reason we are not starting from zero? Why the first available one is the standard output? And again, if we take a look at where is it? The POSIX standard, right? There is std_in file, no. Why aren't we using that instead of this one? Is it because open start from file descriptor 1 instead of 0? Yeah, for now I'm still not sure. Subsequently, writes by the child process to the standard output file descriptor. For example, by routines such as printf, will then be routed transparently to the newly opened file instead of the screen. The output of running the p4.c program. Notice at least an interesting tidbit. RT system call part of a library. It is part of the operating system. Maybe that's more appropriate other than the library. But yeah, is the operating system API considered a library too? Maybe. I mean, from the manual page, it was called system call manual, right? And there is also a header file. So maybe, see, we can call the system call as the part of a library. Maybe. That is an interesting question. like are the system call part of a library? I mean to use, what is it called? To use the fork, I think, I mean, something like this, right? To use the fork system call, we need to include UniSTT header file, which in a way is a library, I think. And if we need wait, we need to call this library to call the wait system call. So to this question, are the system call part of a library? It may be. I mean, again, the definition of library. What is the definition of library in here? So that I'm still not sure, but I assume it is a part of the library that the operating system came with. I mean, the API stands for Application Programming Interface, right? So it is another interface that we can use in our program to interact with the application. And in this case, the application is the system or the operating system. So maybe I can kind of write this API application programming interface, right? And then what is it called? Maybe the system call API is an interface to interact with the system or operating system. Again, I'm creating a hypothesis in here, right? It's an interface to interact with the system or operating system. Yeah, basically the programming interface of an application, right? It is an interface that we can use in another program. Interface that we can use in another program, something like that. Okay. So to answer this question, then maybe system call is a part of the library. I mean, it is an API, right? We can use this interface in another program. It is usually what the library provide, right? Providing an API, something like that. And what is the program in the case of system call? Okay. Is it the program for the program that the API interact with, or the program? I mean, again. Let's split this into two. Program that using the API or program that what is it called? Program that interact that execute the API instruction. Maybe this is what is it called? Yeah, I'm not sure the term. Like the provider, maybe that's the word. The provider or the downstream. Yeah, I'm not sure the term here. Maybe let's call it user program, API provider. Maybe that's it. API provider program. Maybe that's the word. An system call an API backend. As far as I understand, yes, system call is an API, and the program or the provider of those API is the operating system. The provider of system call API is the operating system. Operating system, something like this, as far as I understand. That's why the system called API used to interact, right, with the system or operating system, because the one who execute the API instruction, that another program use, program that execute the API instruction that another program use. Okay, maybe this is the term. I mean, I'm not sure about the official term, but this is the program that we create, right? The user program, and this is the provider program, the provider that provide those API, you know. Provider program that provide API, right? And the provider, as far as I understand, of the system call is the operating system. Okay, that's as far as I understand. Which can be wrong. Again, we learn together, right? Hopefully one day we can verify that. We will see. Okay. You will notice at least the interesting tidbits about this output. First, when P4 is run, it looks as if nothing has happened. The shell just prints the command prompt and is immediately ready for your next command. However, that is not the case. The program before did indeed call fork to create a new child and then run the WC program via a call to the exec VP. You don't see any output print, to the screen because it has been redirected to the file. Second, you can see that when we get the output file, right, and the expected output from running WC is found. Okay, you know what, maybe we will continue this on the next session. So I think that's it for now. Thank you for watching and see you next time. Bye bye.